Any questions about anything? Okay, let's continue our revision. It's going to be quick. Pretty sure we won't cover everything, but let's try to understand the very basics. So today we will look at first law of thermodynamics and the consequent materials. So the idea in first law of thermodynamics was the basic idea was the energy of a system, that is the internal energy of a system, can be changed in two different ways. It can be changed by giving heat to the system. It can be changed by doing work on the system. Heat is random motion. Work is organized motion. So you see over here, heat is when things in the surrounding are just jostling around and moving with each other, colliding with each other, and every once in a while they go and collide with the system and transfer energy to it. And work is when the surrounding is moving up and down or some other organized way, and that leads to transfer of energy to the system. In both cases, if you look at the system, you cannot tell the difference. The system is just going to show an increase or decrease in potential energy depending on what the surrounding was actually doing. So then that was really the basic idea behind the first law of thermodynamics. We talked about isolated, closed, and open systems. We defined them. And so this basically led us to the concept of internal energy, which was our first state function. So the idea was that the change in heat or the work done, they are path dependent. If you go from a point I to a point F, depending on which path you take, the heat and work, W and Q, are going to be different. However, their sum is going to be the same. And that's kind of profound. That is our first law of thermodynamics. That says that the total energy of the system depends only on the variables of state. So the kinetic energy and potential energy. This is a subtle concept which is important to understand, that the internal energy is the sum of kinetic energy and potential energy. Now, the equipartition theorem really talks about the degree, internal energy per degree of freedom. So equipartition theorem does not care whether it's kinetic energy or potential energy. It treats both of them on an equal footing. It says on an average, they will be contributing half kT per degree of freedom. So delta Q is a path function, delta W is a path function. However, their sum is a state function. So delta U does not depend on the path that you take. For each of these possible 4 paths, delta U is going to be the same. And so what does it mean? It means that it depends on the state variables of the system. So you could write it as a function of T, V, and N, or you could write it as a function of T, V, and P, or N, V, and T. Why only 3? Because we know if we know 3, we know the 4th one. At this point, we said that a more natural way to talk about internal energy is to look at it as a function of T, V, and N. Later, that's not natural variables. That is something that can get confusing. Those are not natural variables. Here we defined it as a function of T, V, and N. Later, we talked about natural variables more carefully. Later, we saw that entropy is a function of N, V, and U. And from that, we were able to derive what are the natural variables for U. So right now, we did not talk about natural variables for U. That comes later. So delta U is a state function, delta Q and delta W are path functions, which means you can, in a differential form, you can write down du, while delta Q and delta W have to be written as inexact differentials, or they can also be written as d cut. So, and if you have a problem on this in the exam, you have to be careful about this sign convention over here. This means change in internal energy of the system, heat given to the system, work done on the system. Okay? Wow, Joyce, you look very cold. Are you like on the North Pole or something?
It's pretty cold over here. I mean, it's not terrible, but it's not.
Okay. I'm feeling cold just by looking at you. So now this internal energy can be associated with different modes of movement. We already made it clear it can be potential energy or it can be kinetic energy. And per degree of freedom, we have half kT. So if you have a system with n atoms in one dimension, for example, you could naively write it down as n by 2 kT. If you have a system in 3 dimensions, it would be 3n by 2 kT. When would it be 3n by 2 kT? When it's an ideal system, right? If you have potential energy, things become more complicated. So general way of looking at it is U is equal to number of degrees of freedom multiplied by half kT. And the challenging bit in this is always figuring out the number of degrees of freedom. We did not get too much into detail into this. This is something you will talk about, I think, more in 482, is to look at molecules and think about how many modes do they have and things like that. For now, the important point here is that this number of degrees of freedom does not depend on temperature. It is independent of temperature. It is something that is defined by the molecule or the system itself. If this thing is independent of temperature, then when you differentiate U with respect to temperature, you get a constant, and that is our heat capacity. So if we consider ideal gas, our heat capacity turns out to be a constant, which is true at very, very high temperatures, because at very high temperatures, things tend to behave as ideal gases. I mentioned that this is not true in general. For real materials, you have heat capacity that goes to zero. This was also our first glimpse into heat capacity, which we talked about in detail later. So then we continued our discussion of first law of thermodynamics. That was our first introduction to it. We wrote down du is equal to partial delta q inexact dq plus inexact dw. And I once again want to emphasize this is work done on the system, heat given to the system. And an alternate view of first law of thermodynamics is to look at an isolated system. For an isolated system, delta Q is 0, delta W is 0. Therefore, du is equal to 0. Okay, so then we talked more about delta W. We said that work done on the system can be of different types. The one we are really going to focus on is expansion work, which is work done on the system as it is being expanded or compressed, either way. The sign convention here means that we have to use a minus sign, and F external multiplied by the change in length of the system ds, which amounts to minus P external dV, or delta W when it is work done on the system is minus P dV. That's the take home here. Important point, and this is where the subtleties of thermodynamics start to play in. It is P external. It is not the internal pressure of the system. Internal pressure of the system will be equal to P external if the process is being carried out under equilibrium. Until this point, we had talked about equilibrium in first class, but this is where you all started getting a bit confused because it becomes non-trivial. We are always dangling this P external, and and you can see as per this sign convention, if dV is positive, then delta W is going to be negative. So you are getting work out of the system, right? If delta W was positive, it would have meant you are doing work on the system, but work is obtained from the system during expansion. And that's how heat engines and steam engines work. You expand gas and it causes things to move. And we looked at a practice problem. We went through it. This was the practice problem. Again, go back and look at it. It should be obvious to you at this point. What did we do there? And then I mentioned other types of work as compared to just volume expansion. We could have surface expansion, external extension. We could have electrical work. We could have information work. It's all about the force that is causing a particular change and the amount that is changing. It takes work to gain information. Right now, I am doing information work on you as you are learning information. As you solve your exam problem, hopefully you will be doing work on me because I will learn things from you when you solve problems in a creative way. And wow, this was a long lecture. So here we went back and really focused on the point that this P external is not the same as P of the system. P external will be the same as P of the system, only under mechanical equilibrium. If you have mechanical equilibrium, you can replace P external by P. So if a change is happening reversibly, then you are under equilibrium, and you can replace P external by P. And as soon as you replace it with P, you can use your equations of state. You could have used the ideal gas law, for example, if you have nothing else at your disposal, or you could have used some other complicated equation of state. So, so the reversible change, when we are changing a system and it's going from du is equal to delta q plus delta w, and some change is happening in the system, this change could be happening irreversibly. And at that point, you just have to dangle with P external. But let's say that this change is happening reversibly. That would mean that, first of all, the temperature of the system is kept the same as the temperature of the surrounding. You maintain thermal equilibrium, and you maintain mechanical equilibrium. P is equal to P external at each point. And then you can use your equation of state. We looked at this nice example, so it's worth and going. And this is one of those examples that, so this is in the 916 lecture. We looked at this. This is an important, simple example. Important not because I'm going to give you an exam problem like this, but rather I might, but rather if you understand this, it will help you in remaining of the semester. So here we showed that if we have a system going from volume initial to volume final, and it happens in two different ways. It happens in a reversible way. So you start from this pressure and you reversibly follow the equation of state. Here we assume ideal liquid gas law to come to this final volume. Or it happens irreversibly. You just you suddenly slam down the pressure to the final pressure, and then you allow the, you not slam down. In this case, you suddenly release the pressure to the final pressure, and then you allow the expansion to happen, right? So you can imagine physically there are two things happening. One is in which you gradually release the pressure, and at every stage you allow the gas to maintain equilibrium. And in the other one, you say, whoop, suddenly release the pressure, and then the gas is forced to expand because the pressure has gone down. So we saw that in the second case, in each case, you will be getting work out of the system, right? Because the gas is expanding, and we saw expansion means what can be received from the system. In the second case, the work done by the system or the work obtained from the system is going to be the area of this rectangle. In the first case, the reversible expansion case, the work obtained out of the system will be the area under this curve. And you can see the green area is more than the blue area. Therefore, reversible work is always more than irreversible work. The maximum work you can get out of a system, and this is such a generic philosophical system. If you maintain equilibrium, you can do better. If you drive yourself out of equilibrium, things go funky and it won't work. So it is not possible to obtain more work out of a system than that for a reversible process. And we then talked about heat capacities. The definition of heat capacity is always from heat. It is change in heat with respect to temperature. How much heat do you need to give to a system to increase its temperature by a small amount? If you do this at a constant volume, it becomes CV. If you do it at a constant pressure, it becomes CP. Again, it's worth proving this relation. It's simple. And at this point before your exam, you should be able to show these two. We had not introduced enthalpy. Next lecture, we looked at enthalpy, but both of these relations as to why is partial Q by partial T at constant V equal to du by dt at constant V, and why is partial Q by partial T at constant P equal to partial H by partial T at constant P. You should be familiar with this. And you can see that if it's an ideal gas, then U is equal to some constant multiplied by temperature, and this thing would just be zero. So this clearly shows it would be a constant, not zero. So this is where we did the proof, where we showed that this clumsy thing, which involves path functions, dq by partial t at constant v, can be written down nicely as the derivative of a state function, and that is heat capacity. And there, this is the point that I mentioned, that if you have equipartition, then you are in trouble because it would look like heat capacity is constant, which is actually not true in reality. Okay, good. So then more math happened in next class. In next class, we said U can be written as a function of TVP or a function of TPN or as a function of VPN or something like that, any three variables. At this point, we said, let's work with this notation. And we were looking at constant composition system. Remember, until we got to chemical potential, from this point on in this semester, we really focused on constant composition systems. So we were able to let go of the N most of the time. We did not care about our N. So here I said this representation is the most useful. I did not say it is complete. I did not say these are the natural variables. This is something that used to confuse me when I was a student. But remember, I have not mentioned these are natural variables. So these are just useful. If U is indeed a function of temperature and volume, we can do our partial derivatives magic and write down du as partial U by partial T at constant V, which is CV, and partial U by partial V at constant T, which we defined as internal pressure pi T. This is true for everything. This is true for any system made up of one component. If you have a constant composition system or if you have a one component system, this is always true. We did not assume any ideal gas over here. We did a lot of homework problems where we said that, well, for an ideal gas, pi T should be equal to 0, right? So for an ideal gas, we are left with du is equal to CV dt. And this was quite important, that this happens only for an ideal gas. This does not happen in general. In general, you have to calculate your pi T, and that is hard. So, okay. What did we do? We played around with this concept. We said that, okay, du is equal to delta Q, du is equal to delta Q at constant V. But is there a state function that corresponds to the heat given to the system at constant P? And to show this, we introduced dH, where H was defined as U plus PV. Again, this is this thing, which is 9/18/20. You should go and try to prove to yourself without looking at notes that you can indeed show that dH is equal to partial Q at constant P. If you are unable to show this, your exam might descend into type 2 or lower fun. You should be able to show this without looking up your notes, that indeed dH is equal to delta Q. And so we looked at Cp and Cv, where Cp is partial Q by partial T at constant P, Cv is partial Q by partial T at constant V. And we said, using a physical argument, that Cp must be more than Cv. What was the physical argument? The physical argument was that once you give heat to a system at constant volume, the gas is trapped. It cannot really move any further. But if you give heat to a system at constant pressure, the gas itself will be doing, the system itself will be doing work against the surrounding. So not all of the heat given to the system will lead to increase in temperature of the system. Some of it will be lost in doing work against the surroundings as the gas expands. And remember, expansion work is always gotten out of a system. So this means that you need to do more, you need to give more heat to a system to increase its temperature by delta T at constant pressure than at constant volume. For an ideal gas, again, next class we will do this, but you should be able to do this on your own without any issues, that Cp minus Cv is actually NR. That is a well-defined relation. And much later in your homework problems, you derived, so this was only ideal gas. Much later in your homework problems, you derived Cp minus Cv is indeed given by a very well-defined relation, which I think is quite interesting, that for any material, Cp minus Cv, if you know its thermal expansion coefficient, if you know its volume, and if you know its compressibility. So the thermal expansion and compressibility can be calculated by doing some experiments. And that's amazing because that allows you to connect CP with CV for absolutely any material. And here we looked at a practice problem. The nice thing about this practice problem was that unless you have, if you have a system where some gas is changing into gas, or liquid is changing into liquid, or liquid is changing into liquid plus solid, delta H is almost the same as delta U. The only time delta H starts to be really different from delta U is when you have liquid changing to gas or solid changing to gas, or 3 moles of gas are producing 4 moles of gas. Anytime you see a significant difference, the amount of gas that is being produced in a system, you know delta H is going to be different from delta U. Otherwise, they are kind of similar. That's what we saw this through this and some other numerical example. So I'm going through these things at a hurricane speed for a reason, because I want to cover as many topics as I can. I don't know, I know I won't be able to cover everything. The point being that you can write down on a piece of paper as I'm going through this as to what is it that was not clear to you, and ask questions regarding that on Slack, and I will try to answer them until Thursday night. Friday morning, the exam comes out. I will not be answering any questions starting Thursday when I go to bed, which is around 10 p.m. I won't be answering any questions. Or yeah, Thursday evening is when I will do my last lot of answering. So ask questions by then. Okay, let's move on. We go to 921, and then we will go to 923, and then 925. Yeah, we are covering a month, more than a month's worth in one class, so it's gonna be fast for sure. Okay. This was also an interesting practice problem. So some of you asked me for more practice problem. This is a good one. Again, try to do this on your own. Why is the thermal expansion? Prove that the thermal expansion coefficient for an ideal gas is proportional. What the alpha looks like, just like my proportional. So prove that alpha is 1 over temperature for a perfect gas. How do we show that? It's quite easy. You use the equation of state, and that's what we showed over here. It shows that higher the temperature, less responsive is the gas in terms of volume change. So, oh, I went to the very end of this. Okay, let's come back. So what did we do here? We talked about, this was a pop quiz moment. So that's what I was talking about here, that at constant volume, change in heat is equal to change in internal energy. At constant pressure, the change in heat is equal to change in enthalpy. And the reason why we keep emphasizing these relations again and again and again, because these are path functions, but these are state functions. Ones on the left are path functions, while one on the right are state functions. And that's what makes it so powerful, that because these things on the left are complicated, but things on the right, you can manipulate in so many different ways. Okay, so this was the argument that I made last time, that Cp minus Cv is Nr, and indeed Cp is more than Cv for any material. We looked at that problem. So this class was mostly repeated, it looks like. And we said that delta H is equal to delta U plus delta Ng RT to a fair amount. This was true only for ideal gas, but it gives you a sense. So it's the change in number of gas molecules in the reaction that matters. Okay, we did a bunch more manipulation with U, and this is the thing. So which class is this? This is 921, and you should try to show on your own without opening notes that thermal expansion coefficient for a perfect gas is 1 over temperature. This is a good practice problem to make sure that your engines are running correctly. Okay. So next class, again, we did a bit of recap. We introduced isothermal compressibility. And I think I re-emphasized, because this was so important, it looks like I re-emphasized many, many times that dq is equal to du, constant v, and dh is constant p. Okay, then, so we talked a little bit about change in internal energy, and where we said that we should look at internal energy as a function of temperature and volume. It's useful. We did not call it natural variables. We said it is useful. Similarly for H, we looked at constant pressure and temperature. And there we said this means dH is equal to partial H by partial P at constant T dP is partial H by partial T dP constant P dt. This page is, which class is this? This is 923, page 3 in my notes. You should spend some time going through, because here for the first time we used a complicated relation from partial derivatives, which are easy to forget, and they might just show up in any of your exam problems, and you will be stuck if you don't realize what is to be used here. It is this cyclic identity that if H is a function of P and T, you can write down this product involving all three partial derivatives, and that product must be -1. Thing to keep in mind is everything shows up in the numerator once, everything shows up in the denominator once, everything shows up in the constant thing once. So it's kind of beautiful. It's really symmetric. We use this to write down dH is equal to Cp dt minus mu Cp dP. Mu Cp dP, we derived this relation. This could be something, just to give you a flavor of how the final exam might look like. There could be a problem where I just ask you to derive, show that dH is equal to Cp dt minus mu Cp dP, where mu is partial T by partial P H for any gas. And then you have to work through and do this on your own. So this could be a typical exam problem. That's why I said this is important. We talked about Joule-Thomson coefficient and isenthalpic processes. This was interesting, where we showed how to create an isenthalpic process. And here we really proved as to why does this happen. The idea was that gas molecules are either very close to each other, to equilibrium, so their potential energy is, at high pressure, they are close to each other, so their potential energy is lower. At low pressure, they are very far from each other, so their potential energy is higher. And we connected this to the change in temperature. This was the main idea in this thing. Okay, we talked about thermochemistry. This part was exenthalpic and endenthalpic processes where delta H less than 0, delta H more than 0. And this, I have to be careful because this always takes me to the end of the notes. Okay, next class, there was again a pop quiz. I just wanted to make sure that you realize that if H is a state function and U is a state function, then H plus U is a state function. So is H plus 2U. So is H plus cosine of H divided by some constant. You can add state functions to each other. A sum of a function, a product of a function, they are all still state. A product of state functions or sum of state functions are still state functions. That was the idea. And again, I had asked you this thing. I think this thing showed up in so many pop quizzes, that Q is equal to delta H at constant P and Q is equal to delta U at constant P. At this point, we had looked at isochoric processes where the volume is constant. We had looked at isobaric processes where pressure is constant. We had looked at isenthalpic processes where enthalpy is constant. Now we looked, and we had looked at, of course, isothermal processes where temperature is constant. Here is, I'm not going to do it as a proper pop quiz, but I just want you to think at this point and tell me, what is du for an isothermal process? Anyone wants to answer? For an isothermal process, what is the change in internal energy? Any ideas? Are you sure, Elizabeth? You answered first, so I'm going to ask you first. Can you unmute yourself? Are you sure du is 0? Did I say ideal gas?
No.
So be careful, right? That was the whole point. du is equal to Cv dt for an ideal gas, right? Hence, du is equal to 0 for an ideal gas. But for a non-ideal gas, du is equal to Cv dt plus pi t dV, and this internal pressure is non-zero. So du not equal to 0 in general for an isothermal process. This is something you should hardwire into your brains, or you really can't hardwire. Yes, that would be creepy. But that du is not zero for an isothermal process. Only for an ideal gas is du equal to zero. Isothermal means dt is equal to zero, period, nothing else. Okay? An adiabatic process is defined where q is equal to zero. So if q is equal to zero, it means that you write down, sorry, the first law of thermodynamics that gives you delta u is equal to q plus w. Since q is zero, delta u is equal to w. So the change in internal energy is equal to the work done on the system in an adiabatic process. Ideal, non-ideal, anything, it's always true. We can calculate this. So we are saying du is equal to delta w. This class is also very important for fundamental things, this 9, 25, 20, because here we calculate du. And again, it's written right here, the question that I asked you, du is equal to cv dt plus 0 dv for an ideal gas, right? So here we assume, we focused on an ideal gas. For an ideal gas, du is equal to cv dt. So we can actually calculate, and it's an ideal gas, so we can use pressure is equal to nRT by V, and we can calculate, we did all of this, and we calculated the temperature volume profile for an ideal gas undergoing adiabatic expansion, and we got TV to the Vt to the power constant is equal to Vt to the power C is equal to constant. This for adiabatic expansion of an ideal gas. This is not going to apply to a van der Waals gas. This was one of the midterm or homework problem, something where you had been given a van der Waals equation of state. So I want to point out here, look at midterm where you had a van der Waals equation of state, where many of you just substituted this as V minus NB and tried to go ahead, which was wrong. You had to work through all of this for the van der Waals equation of state and then get the answer. So this is this 9, 25, 20 exercise of calculating the equation, the profile, the temperature volume profile for adiabatic expansion of an ideal gas is a good exercise. Try to also do it for van der Waals gas. Try to play with it, see what you will get for a virial equation of state, okay? And similar to that, Tv to the, so yeah, this just gave us V to the power, Vt to the power C is equal to constant, which is equivalent to writing Pv to the power gamma is equal to constant, because you can manipulate temperature and get rid of temperature and substitute it with pressure using the ideal gas equation. We talked a little bit about thermochemistry. This was quite simple because you had all mastered state functions by this point. The idea here was that if a reaction is going from A to B to C to D, and if you're interested in seeing whether A to D will be isenthalpic, you can break it into chains. So if you just have a reaction going from A to D, and you imagine some other sequence where A goes to B, goes to C, goes to D, you can calculate the enthalpy change for these other sequences and sum it all together to talk about the enthalpy change in going from A to D. You could not have done this for the heat difference, but you can do it for enthalpy difference because it's a state function. Okay, let's go to 928. We talked a bit more about typical forms of enthalpy change. We talked about enthalpy change of fusion, vaporization. Sublimation is going to be a sum of fusion and vaporization just from the argument in last class. This was quite easy. I'm going to skip this. I want to get to the beast, the second law of thermodynamics. Here the point was that du is equal to delta Q plus delta W, but it doesn't tell us whether a ball bouncing on the ground and gradually coming to rest. In this case, you are changing internal energy of the ball and of the ground, and you are doing work against, or gravity is doing work on you, and heat is being released to the surroundings. So you can write down your first law of thermodynamics and you sum up everything. You will see that the ball falling down, the heat being lost to the ground and as the ball is hitting up as it falls down, everything is fine. First law of thermodynamics is followed. But the first law of thermodynamics would be followed for the opposite process also. If the ball suddenly started sucking heat from the ground and started to jump up, converting heat into potential energy, and it jumped up, that would also do first law of thermodynamics. In other words, If delta U is equal to delta Q plus delta W for some process, let's say the ball falling, then the ball rising minus delta U is equal to minus delta Q minus delta W also follows first law of thermodynamics. Nothing is stopped. But we know that this is not true. The balls don't suddenly start jumping up, right? This led us to the concept of spontaneous or spontaneity or even feasibility. So first law of thermodynamics tells us that a process is spontaneous. First law of thermodynamics does not tell us about spontaneity. It tells it is feasible. It does not tell us whether it's going to happen on its own or not. Examples of spontaneous processes are time moving forward, ice melting, mind losing hair, of course, and your room getting dirtier. And all of these, their opposite, time moving backwards, is also actually allowed by first law of thermodynamics. There is nothing stopping it. The second law of thermodynamics is needed to say that these are the preferred spontaneous directions. And to do this, we introduce different formulations of second law of thermodynamics. Some of you asked me to go over this in the Slack, so that's what I'm doing now. The most mathematical form of second law of thermodynamics, which I did not really do in this semester, is that there exists a state function S given as there exists a state function whose natural variables are n, v, and u, which is maximized. But this is Chem 684. We are going to ignore this optional form. Let's go to Kelvin's statement. Kelvin's statement says that no process is possible spontaneously in which the sole result is the absorption of heat and its complete conversion into work. You cannot just consume food and become so efficient that you start running all the time and all the energy is just converted into, all the food is converted into energy. It's not going to happen. Batteries, for example, or photosynthesis in nature, when sun's energy, solar energy, and other things are converted into plants' chemical energy, I think the efficiency is around 15% or 20%. You are not completing fully the solar energy into work. That was Kelvin's statement. And it's okay if you forget whether which one was Kelvin, which one was Clausius, that doesn't matter, but you should remember the impact of this statement, which is that it is not possible to completely convert heat into work. The other statement, Clausius' statement, says that heat does not spontaneously flow from a colder body to a hotter body. So Joyce is wearing a big ass jacket. She cannot just go and sit out in the cold and say, come heat, come to me from the outside. It's not going to happen. Second law of thermodynamics prohibits it. And both of these statements are equivalent. We will look at that in a moment. And that's something we did in next class. So let's go to the next class, which is 9:30, then 10:02, then 10:05, then 10:07. Okay. So we go to 9:30. So I don't know what I was. Oh yeah, this was one of those problems on homework 3, which was really painful. I think the ones of you who really like math, like Matt, I think Matt Laskowski is there. Matt really likes math. So Matt had a great time in this problem, but otherwise I thought it was a very complicated mathy problem. You might have one problem like that in your exam, so be ready. So what was I talking about here? I was reminding you that organized motion. Oh yeah. So another way of thinking about second law of thermodynamics is that it is okay to spontaneously change organized motion into randomness, but you cannot spontaneously change randomness into organized motion. Organized motion can, however, change into randomness. In other words, what is organized motion? Work can change into heat, but randomness, heat, cannot change into work. So it's useful that we just went over the very beginning part of the semester, because that's what we just discussed there, right? That work is organized motion. Nature prefers randomness. It prefers a direction of change that leads to dispersal of energy. Nature wants energy to be distributed in as many different ways as possible. Nature is, yeah, let's not get political here. I would have said nature is democratic, but anyway. So Kelvin's statement says, no process is possible in which the sole result is absorption of heat from a reservoir and its complete conversion into work. Clausius statement says heat does not spontaneously flow from a colder to a hotter body. So Kelvin's statement can be written diagrammatically in this form. We have a hot source at T is equal to T2. You have a motor, and this motor is so efficient that it takes the heat from the hot source and changes it into work 100%. This is not going to happen. What is, however, possible is that the motor dissipates out some energy. It has to give heat out to a cold sink. And then you will get work out of the system, and you can define the efficiency of the system, which is, and I used a modulus sign here to keep things simple. You take in Q in heat from the hot source, and you produce work. So the ratio of work by Q in is the efficiency, which is less than 1. Oh, before I forget, super important. The course evaluations are now out. 20 of you have already submitted them. The others, please mark it. Please try to do it when you can. It's important for at least 2 reasons. Number one, it's very important for me to get, it's anonymous. So I get a sense from what could have been done differently. Although this semester is so different, next time I teach 481, it will probably not be an online class, but who knows? I mean, who knows? It's still useful to have your feedback as for me as a teacher. And secondly, when I come up for promotion in 2 years from now, they look at your feedback. They want to see if students, they don't go and check Planet Turp or rate my professor or things like that. They look at these anonymous feedbacks. And these feedbacks are important. I'm sure some of you are unhappy the way I taught it, because it's very hard to teach in a way that is exactly right for 99 different students. It's simply not possible. It's as much as I would have liked to please all of you and for all of you to learn equally efficiently, it's not possible. Some of you probably felt Slack was uncomfortable. Some of you felt maybe there should have been more Slack. I don't know, but I still want to see how you felt. So please fill it up. And I think I mentioned that I can, but I won't be releasing the final until I reach a certain amount of course evaluation. It's like 80 or 90%. I would like to make sure that this many of you have submitted your feedback. We are still at 20%. So please try to do it. It won't take more than a few minutes. Okay, great. Let's get back to science. So, so this efficiency is going to be less than 1. It cannot be equal to 1, because that would mean that all of the heat that you took from the hot source has been converted into work. That's not going to happen. So there is always a cold sink in which heat is dissipated or is wasted. So first law does not distinguish whether we had a cold sink or not. It doesn't matter for first law. So at this point, we had not yet talked about entropy. Then we introduced the notion of entropy. This is not third law of thermodynamics. This is third statement of the, oh, my screen froze. That's terrible. So at this point, we had not introduced the notion of entropy, but we do that now. And in order to do that, we introduce second law of thermodynamics in a third form. This third statement says that entropy of the universe, entropy of an isolated system, that is system plus surrounding, must be increasing in course of a spontaneous change. And we then showed that Kelvin is the same as Clausius, which is the same as this third statement, which is the same as Clausius. All 3 things are the same. There were 2 ways to define entropy. One is the molecular way. I'm not going to be asking you questions on the molecular way in the exam. It says S is equal to K log W, which is the number of ways of arranging the system. You will be using this molecular way in 482. That's why I introduced it. It's not complicated. You just have to calculate W, number of ways in which you can arrange the system, and take its natural log multiplied by Kp. What is more important and actually harder to get is the classical way, which says that the work done on a system depends on path. Even if you do it reversibly, it depends on path. It's always going to depend on path. But if you divide it by the temperature, then it becomes path independent. ds is equal to delta q reversible by temperature is path independent. So for these different paths and going from I to F, all of them, if you just integrate delta q reversible, if it was irreversible, of course it's different, but if it's reversible, it's still different. However, if at every point you calculate the temperature, which might be changing, divide by that and then integrate, you get a path independent function. That's our change in entropy. It is integral delta q reversible by T. These two definitions are equivalent. Macquarie's book talks about it. We did not go into it. So this was 9:30. Now we go to 10:02. We are in October now. So we calculated the change in entropy for a few example processes. We calculated the change. So this is also good practice exercise on 10:2. We calculated the change in entropy for a perfect gas undergoing reversible isothermal expansion from volume Vi to Vf using this formula. And we got an answer, which is nr ln Vf by Vi. And what did we do then? At this point, and so we had already drawn a picture for Kelvin statement, which is you're taking heat from a hot source and converting it into work completely efficiently. And we showed that this is consistent with our third statement. We calculated delta S and we showed that this is going to be negative in this case. So if this process happened, the change in entropy of the universe would be negative. Therefore, it cannot happen. They are equivalent. Same thing, we drew a picture for Clausius where we had cold at T2 and we showed that heat spontaneously flowed from T2, the colder one, to the hotter one. And here we showed that once again, it would mean that delta S for the full thing, for the universe over here, is negative. So everything is consistent with each other. We had not yet proven that S is a state function. In order to prove that S is a state function, we first looked at an example. So this example is useful. This is 2nd October, page 4. We looked at an ideal gas undergoing changes in 3 different ways: pathway A, pathway B, and pathway D plus C. So pathway A, pathway B plus C, and pathway D plus E. Isothermal, adiabatic plus isochoric, and isobaric plus isochoric. We calculate the entropy change for all 3 of these. And again, this is a wonderful practice problem because one of these entropy changes was non-trivial. You had to use the equation of state for the gas. I could easily make an exam problem where I have you do this not for an ideal gas, but for a van der Waals gas. And if you're not totally clear on how to do this, you would trip on that. So we did that and we showed that indeed for all of these 3 paths, the entropy change is constant, but that was not a proof. That was an illustration that maybe entropy is a path function. Then in order to do this, and we kept talking about this in the next class, that's what I meant. We had to use this relation for the equation of state in order to do this correctly. We spent a lot of time over this and we looked at a numerical example. That's what we did in this class. Then we talked about Carnot cycle. How did we do Carnot cycle? In Carnot cycle, the idea was 3-step. We showed that first of all, we showed that the change in entropy along a cycle in going from a certain point and coming back to that certain point is 0. That was what we wanted to show. We showed that this is true for a special cycle of moves called a Carnot cycle for a perfect gas. Then we showed that this means it must be true for Carnot cycle for any material. And then we showed it must be true for any cycle for any material. Pakra is in the mood. This is where I'm going to stop now. I want you to go through this proof for the Carnot cycle. If you have a question about this, I will answer this on Slack. And after that, in next class, I'm going to continue from this point onwards in second law of thermodynamics. Next class will be last revision class. I will be having office hours today, and keep asking me questions on Slack. And again, those of you who are feeling confident, take time to answer questions for your classmates. Once again, teaching others is a very good way to learn. I will also be answering, but sometimes I'm late. So those of you who are confident, please answer other questions. The exam will be released Friday morning. That's when Slack will stop. This Friday morning. Their next class is the last Zoom session we are going to have for this semester. After that, Friday morning exam goes out and you have exactly 1 week to do it. Okay, so see you in office hours at 11 a.m. today.